Welcome to The Explainer. Today, we're diving into the secret life of a microchip. We're going to follow its entire journey, all the way from just a concept, a line of code, to the actual physical piece of silicon that literally powers our modern world. It is an absolutely mind-boggling process.
So you have to wonder, how do they do it? How do you take an abstract idea, a blueprint that exists only on a computer, and turn it into a real, tangible object with parts so small they're measured in nanometers? Well, it's an incredible story of managing insane complexity with some of the smartest software tools on the planet. All right, here's our game plan. We'll start with the digital blueprint, run it through the synthesis engine, see how it becomes a physical reality, and then do a final pre-flight check before we wrap up. Let's get into it.
Okay, so first things first. Every single microchip out there, every single one, doesn't start as a thing. It starts as an idea, a plan written out in what's called a hardware description language, or HDL.
So how do you actually write the blueprint for a chip? Well, designers mainly use one of two languages, Verilog or VHDL, which you see right here. Now, these aren't like the programming languages you might be used to. They're built to describe physical hardware. So instead of describing a program, this code is describing logic gates and the tiny wires that connect them to do a job. In this case, something as simple as adding a few numbers together.
Let's be real, today's chips are way too complex for any one person to design from start to finish. So to manage all that, engineers use clever tricks like a logic abstract. You can think of it like a placeholder, a black box that basically makes a promise. It says, hey, some logic is going to go here, my team is working on it. This is what lets massive teams all work on different parts of the same chip at the same time, all trusting that in the end, everything will connect perfectly. All right, so we've got our digital blueprint, it's written in code, but that's still just text. How does it become an actual circuit plan? Well, this is where the magic really starts to happen. A process called logic synthesis kicks in. It's this incredibly powerful software engine that translates the abstract language of that code into a concrete circuit made of real physical components. And this synthesis process, it's very systematic. First, the tool elaborates the design, just figuring out the high-level structure from the code. Then, it applies constraints. These are the rules of the game. Things like, this calculation has to happen in less than 2 nanoseconds, or this part of the chip can't use more than 5 milliwatts of power. Finally, it translates all that logic into a network of standard parts and optimizes the whole thing to make sure it meets every single one of those targets. It's a massive juggling act.
And this is a really, really crucial point. Designing a modern chip is an intense balancing act. It isn't just about making the logic work. It's about making it work inside a super strict power budget. Every extra milliwatt of power creates heat, and it drains batteries. So controlling every little bit of it is absolutely critical. So to manage that power, designers get extremely specific. They use a file, something like this common power format, to map out what they call power domains. Just look at this table. In active mode, different parts of the chip are getting very specific voltages. But to save your phone's battery life, they can switch the chip to a sleep mode, where they can shut down the power to an entire section of the chip completely. Now, inside that design code, you find way more than just simple logic gates. You find some serious math. This function you see here, $blend, it's basically a recipe for a really sophisticated piece of signal processing. We're not just adding A to B anymore. We're doing a much more complex calculation that the chip needs to perform, and it has to do it incredibly fast. But here's the cool part. The designer doesn't have to build that complex function from scratch. The synthesis tool is smart enough to analyze that function, look at the timing, area, and power rules we talked about, and then automatically pick the best possible architecture from its library to build it. It might pick a slow one, a medium one, or a really fast one, whatever is the most efficient choice for the job. Okay, so now we have our logical plan. It's a netlist, basically a giant list of gates and connections. But that's still just data on a computer. The next step is huge. We have to create a detailed physical layout that the silicon factory, the fab, can actually use to manufacture the chip. And this is where two really important file formats come into play, LEF and DEF. The easiest way to think about it is with Legos.
The LEF file is your catalog of all the different Lego bricks you're allowed to use. It describes the physical shapes and sizes of all the standard parts. The DEF file, on the other hand, that's the instruction manual. It tells the factory exactly where to place every single one of those millions of bricks and how to route all the tiny wires to connect them.
And I mean, when you look inside these files, the level of detail is just wow. This little piece of code from a left file is defining the geometric rules for creating vias. Vias are the tiny vertical tunnels that connect the different layers of metal wiring that are stacked on top of each other in a chip. Every single aspect of the physical shape is spelled out with perfect precision.
We are so close. The design is logically correct, it's physically laid out, but before we hit the big red button, before we tape out the design and commit millions of dollars to manufacturing, there is one last, absolutely critical step. We have to make sure that once the chip is made, we can actually test it for flaws. This whole field is called Design for Test, or DFT. Why? Because if there's even one microscopic flaw on that chip, the entire thing is just a very expensive piece of sand. So you literally build a special test system directly into the chip's circuitry. You can think of it like a separate nervous system, whose only job is to help testers find those tiny, hidden flaws. This test circuitry uses all sorts of specialized structures, but the most important are called scan chains. It's a really clever idea. They link all the chip's internal memory elements together, one after another, into these long daisy chains. During testing, a machine can use these chains to shift test patterns in and shift the results out. It basically acts like a special kind of X-ray, letting you see deep inside the chip to find any faults. And you might be wondering, who on earth wires all this up? Well, this isn't done by hand. The design software automates this whole thing. It intelligently stitches those scan chains together and then verifies that the final design follows thousands of complex testability rules. This little bit of output here is the tool reporting back that it found 60 cells that are perfect candidates to be part of that test nervous system. So there we have it. We've gone from a simple line of code to a complete, physical, and testable design that's ready to be sent to the factory. But, as you've probably guessed, in the world of semiconductors, the journey of innovation never, ever stops. It just gets more intense. This whole process is constantly evolving. I mean, the chips are getting so incredibly advanced that even the rule books, the standards themselves, have to be rewritten. The recent update to version 6.0 of those LEF and DEF files we talked about, it added all new rules just to handle the challenges of building chips with features smaller than 32 nanometers. We're pushing the absolute limits of physics here.
Which kind of brings us to a final big question to think about. As we keep pushing these boundaries, as chips get exponentially more complex, maybe the biggest challenge isn't just the silicon anymore. Maybe the true frontier, the real cutting edge of innovation, lies in the increasingly brilliant and sophisticated software that lets us manage all this complexity in the first place and turn these wild ideas into reality.